Hello everyone, welcome to Algo-holic, the place where you learn not just the solutions but the thought process behind solving problems. We are starting off with the most popular problem on LeetCode, the two-sum problem. Here we are given an array of integer nums and an integer target. We are supposed to return the indices of two numbers such that when we add them up, we get the value target. Now this is a problem that most people will at least be able to solve using a brute force approach. If not, let me write it down so that it'll be easier for you to visualize. So we have two unknowns, we add them up and we are supposed to get the value target. Now let's denote x and y representing the two unknowns. Now how many values can x hold? Now there are n possibilities because there are n elements in the array. The same thing applies for y. Y can hold n possibilities. Now if you have to check for every combination of x and y, what do? For x, we run a loop from I is 0 up until n minus 1. We do the same thing for y where we start from I plus 1, run it until n minus 1. All you have to do now is put an if statement inside the two loops to check for the result. Now, what is the time complexity of this? The first loop runs n times. The second loop runs n minus 1, n minus 2, and so on times. If you simplify that, it's n minus 1 by 2. You can round it off to big O of n squared. Now, this is not the most optimal solution, but it's a good start. Now, where do you start with optimizing the solution? If you think about the pointers in the first solution, there's I and j, they start from the leftmost position and they move towards the right, checking every possibility of x and y. Now, wouldn't it be much more efficient if we start I at the leftmost position, we start j at the rightmost position, and we skip certain combinations? Now, how do you know what combinations to keep and what combinations to skip? Now, we need to have some sort of idea of what the array looks like to make that decision. And we don't know anything about the array. So that's when sorting comes into play, where we sort the array and we use the property of a sorted array to make that decision. For example, let's say we have an array like 1, 5, 20, 50, and 100. So it's a sorted array. And let's say the value of t is 55. Let's start the I pointer at 0th index. Let's start the j pointer at the last index. Now let's add them up. We get the value 101. Now, is 101 more than 55? Yes, it is. Now, which pointer do we move? If we move the I pointer towards the right side, we definitely know that whatever sum we get is going to be more than 101 because every element to the right of I is more than I. So 101 is the least that we could get. So we cannot move I. Now let's try moving j towards the left. If we move j towards the left, we know that we'll get a value which is less than 101 because every value on the left side of j is smaller than j. So that's how we decide which pointer to move. So let's move the j pointer towards the left, and j is pointing at 50 right now, and I is still in the same place. So we add them up, we get 51. Now 51 is less than 55. If we move the j pointer towards the left even further, we're going to get a value which is less than 51. So we don't want that. We move the value I towards the right. Now I is pointing at 5, j is pointing at 50, we get the value 55. Now this is the answer. But there is a catch over here because we got the values 5 and 55 which add up to t. But in the question, it's asking us to return the indices and not the values. Now, how are we supposed to get the indices of a sorted array? Because we practically changed the indices when we sorted it. So how do we go back? Well, the answer is that we cannot. So we need to store these indices and its corresponding values before we sort the array. For example, let's say the array before sorting was 20, 5, 100, and 50. Let's say this was the array before it was sorted. Now what we need to do is use a hash map to store the values and its indices. For example, 20 is the 0th index, 5 is the first index, 1 second, 100, 3, and 54. So after this, once we get the answer, which is 5 and 50, all we need to do is look up and get the answer. So the answer is going to be 1 here and 4 here, which is the final answer. Now, what is the time and space complexity of this? The time complexity is going to be n log n because n log n is the average time it takes to sort an array using an efficient algorithm like merge sort, quick sort, or heap sort. Now, the space is going to be n as well because we need to store the indices in a hash map, so space is going to be n. Now, this is a better algorithm than the first algorithm. Now, can we do better? Can we do better than n log n? We can, and how you arrive at that is by manipulating this equation and using the properties of a hash map. Now, what do I mean by that? In the brute force approach, what we were doing is that we assume a value for x, and then we loop through the array to get the value of y, which adds up to t. For example, if x was 5 and t was, let's say, 7, we are checking the array if the array has an element 2, because 5 plus 2 is 7. So instead of this, can we somehow store the value 2 in a hash map so that we don't have to look at the array every time? So since now for checking inside the array, it takes O of n time, but fetching an element from a hash map just takes O of 1. So by eliminating O of n in the equation, we can reduce the time complexity to just O of n, because it just becomes O of n into O of 1 instead of O of n into O of n. So that is the whole idea behind this. So let me show you how this works with an example. So let's say the elements are 5, 20, 50, 100, and 500. And let's say the value of t is 120. Now we have a hash map over here. Now let's assume the value of, let's check with the value of x. Now we got the value of x, which is 5. That's the starting point basically. Now what should 5 be added to get the value t? As in, what should be the value of y if it is present in the array? So 5 should be added with 115 to get the value 120. So we don't know if 115 exists in the array or not, but let's just keep 115 in the hash map now, so that when we get to the point where 115 is encountered in the array, we can get the answer. So that is the whole idea. So we got 5, we have 115. Now what is the value of 115 in the hash map? We don't want to lose the index like the previous sum, so we just put 0 over here, which is the index of 5. Now let's go to 20. Does 20 exist in the hash map? No, it does not exist in the hash map. We'll just put 20, but again, we can't put 20 directly because we are putting the value of y, not the value of x. Currently, the value of x is 20. So what should x be added to get 120? The answer is 100. So 100 is basically the y here. So we'll put the index as 1. Now let's check for 50 over here, x. Now what should 50 be added to get the value 120? 50 should be added with 70. 70 would be the y value if 50 is chosen as x. So we put 2. Now we check if 100 exists in the array. 100 already exists in the array, so we have gotten the answer. That is how it works. Basically, if you are good at math, you can visualize it using this equation. The equation is x plus y is equals to t. What we are doing is we are just making it y is equals to t minus x. So this is how it works. Now once we found the match, what do we do? We found the match over here. We take this index, which is 1, and we take the index of 100 over here. So that is 0, 1, 2, 3. So this will become 3, and this is 1. This is the final answer. Now what is the time complexity of this? We are just looping through the array once. So that's O of n. And we are taking O of n space again because we need to store the values in a hash map. So this is the most optimal solution. So let's quickly code up the brute force solution. So for I in range length nums, j starts from I plus 1 and goes till the end. Now we just need to check the sum. Return the indices. So this is pretty straightforward, and I don't think I need to explain the code further. I'm going to explain the next solution, the two-pointer approach, and this might seem a bit more complicated, but you don't need to come up with a solution in an interview. It's just good to know. It's just good to know different ways of solving a problem. So first we are sorting the array, and before we sort the array, we need to store it in, we need to make sure that we don't lose the indexes. So again, to sum it up, for example, if we have something like 3, 2, 4, in the dictionary, it's going to be something like 3, 0. 0 is the index, 2, 4. So this is what we're doing right here. And there's also an edge case. For example, if you have repeated elements in the array, what is going to happen is that in the first iteration, it's going to be 3, 0, and then in the second iteration, it's going to be 3, 1, and it's going to be replaced. So we don't want that. And the only way to avoid this is to make sure that this is an array. So I'm going to show you how to do that as well. So first we check if value already exists in the mapping. If it already exists, we just need to append it. If it doesn't, we'll just add it. So that's about it. So we've created the mapping, we've also sorted it. Now it's time to take care of the pointers. Left starts from 0 and the right starts from the last element. While left is smaller than right. This is not going to overshoot, but it's just good practice. So nums left plus nums right is more than target. That means we've overshot it and we need to decrease the right pointer. If it's less than the target, we need to increment the left pointer. Else we found a match and we need to just pop it out of the array. So while 1, while 2 is equal to indexes nums left. If I think this is the correct code. So yeah, this should work and we just need to return it. So there's a problem, give me a minute. Indexes, oh sorry, it's mapping. So yeah, this also works. And let's look at the optimal solution, which is a bit more easy to code up. So we'll again create a mapping, and this time we're going to store the difference. So for example, if you have something like 5, 8, 2, and let's say 1, the mapping hash map will be storing the difference between the target and each element. So let's say the target is 9. The target is 9. For 5, it's going to be 4, 0. For 8, it's going to be 1 and 1. For 2, it's going to be 7 and 2. For 1, it's going to be 8 and 3. So this is how we are going to store the mapping. So so this is the key of the mapping, which is target minus the value, and we just have to store it in the mapping. And we're storing the index here. Now, before we store, we need to make sure, we need to check if the value already exists. So if value in mapping, just return the index. Return the current index as well as the mapping's value. Yeah, yep, this should be it. Yep, this is the most optimal solution. And as you can see, it's pretty efficient. I don't know, there seems to be some problem with the LeetCode servers, I guess, but yeah, it's the most efficient solution. Yep, there you go. Let's quickly look at what the code looks like in C++ and Java. In C++, instead of using a dictionary, we use something called an unordered map. And the logic remains the same, where we use one for loop, we subtract nums from target to get the key, we check if the value is present in the hash map. If it is, we return the indices. If it's not, we add it into the hash map. Java code looks pretty much the same, where you have the hash map, the for loop, subtracting nums from target to get the key, checking if the value is already present in the hash map, and return and adding it to the hash map if it already isn't present. So that's about it. I hope you found this video helpful. Your feedback helps me make better content, so please share your thoughts in the comments below. I'll see you in the next video.